Hey everyone, hope you are doing well on this fine Wednesday morning. So, we're going to continue on today talking about 6.3 periodic trends. Hopefully, yesterday you watched it and you sort of understand what's going on with atomic radius. Um, so, we're going to continue on today talking about the last few periodic trends, the last three. So, yesterday we talked about describe trends among elements for atomic size, which is the radius, explain how ions form. Today we're going to talk about trends for ionization energy, ionic size, and electronegativity. And we're going to state what those things mean, okay, and how they're important to organizing the periodic table. So I'm going to try to click through this without having this play too much. Okay. All right, so we went through all of this. Okay, so we went talked about atomic radius. Atomic radius decreases as you go left to right on the periodic table, and it increases as you go down the periodic table. And we explained why. As you go left to right, if you remember from yesterday, as you go left to right, you stay in the same shell, the same principal energy level, but you add protons. So you increase the positive charge of the nucleus, which brings in the negative electron cloud closer to the nucleus. So that's why the atomic radius is decreases. And as you go down, you do increase an atomic number, but you add more shells. You add an energy level as you go down, and that matters way more than the addition of the extra protons there. So you're adding more shells, it's getting larger. The um, radius is. All right, so here's where we're going to start today. So we're going to talk about ionization energy and what ionization energy is and why it is important for you to understand. Okay. So the question asks, what are the trends among the elements for first ionization energy? And so here I got a nice meme of Vegeta, and also I have a short video that you can watch if you want to see the reaction between sodium and chlorine, which is related to what we're going to talk about today. So I'm going to skip over that for right now, though. Okay, so electrons can move to higher energy levels when we absorb energy. And we talked about that last unit. When you go from n equals 1 to n equals 2, you absorb energy. And sometimes the electrons have enough energy to overcome the attractive forces of the nucleus. And the energy that's required to remove an electron from an atom to make an ion, that's because that's what you do, is called ionization energy. Okay. So some elements, such as metals, the left side of the periodic table, they want to lose their electrons. So they're going to have lower ionization energies generally than the elements on the right-hand side. This energy is measured when an element is in its gaseous state, okay? And the energy required to remove the first electron is called the first ionization energy, okay? So here's the trend. First ionization energy tends to decrease from top to bottom. So it is the opposite. This one is the exact opposite of atomic radius from yesterday. So ionization energy decreases from top to bottom and increases left to right across the period. Okay, opposite from yesterday, but let's talk about why this is. Okay, here's a chart you can look at with the different values. It's not really going to help you. But ionization energies can help you predict what ions an element will form. Next unit, we start talking about the valence electrons per group, and we start talking about the charges of the ions per group, which is very, very important to understanding how elements combine together in chemical reactions. Okay, so group 1 metals tend to form ions with a +1 charge because they have one valence electron and they want to lose one valence electron instead of gain 7. Okay, we'll talk about that though next unit. So here is the trend. If you already wrote that, you don't need to write it again. First ionization energy generally, I can't talk, it decreases from top to bottom. Okay, so let's talk about why. So we know if we go down the periodic table, the atomic radius gets larger. Okay, and as the atomic radius gets larger, okay, the nuclear charge has a smaller effect, as you can see right there, on the electrons in the highest occupied energy level. Basically, it's easier to remove an electron that's farther away from the nucleus than it is when it's closer. And that makes sense, right? Think about magnets. Okay, it's harder to pull a magnet off something or attract something that's closer to another magnet than it is if it's farther away. Same as like if you go, imagine you're at a concert again. It's easier for you to leave Think about this. Think about if you are parked, you go to Walmart, okay, and you park at the very end of the parking lot. Okay, it might take you a while to get in the store, but to leave, to get in, once you get in your car, leaving is a lot easier than it is if you're in the very front having to maneuver around all the people there. So it's easier to remove an electron if the radius is larger, and the radius increases as you go down because it's farther away from the positively charged nucleus. You are removing something negative um, from the atom, right? And it's easier to do that if it is farther away from the nucleus, the protons, okay? So the ionization energy is going to be lower. It's going to require less energy for you to do that. So here's the other trend. It increases from left to right across a period. And this can be explained by the nuclear charge and the shielding effect, which we talked about yesterday. Okay, as we know, as we go left to right, the nuclear charge increases. Nuclear charge, all that means, as I said yesterday, all that means is that the charge of the nucleus is going up. Okay, because in the nucleus we only have protons and neutrons, and neutrons don't have a charge, protons do. So the positive charge of the nucleus is the nuclear charge. Okay, so if you stay in the same period, you're in the same shell. Okay, and so your atomic radius decreases, as we mentioned yesterday. Well, when that decreases, as we talked about yesterday, what happens there is it's going to be harder to remove an electron because it's more attracted to the nucleus when it's closer to it, and it's pulled in closer. That's why the radius is smaller. So it's harder to remove that electron. Okay. So as a result, there's an increase in the traction of the nucleus for an electron. So it takes more energy to remove it. Okay. It's like if you're trying to take a piece of candy from a baby. It's a lot easier to take a piece of candy from a baby than it is to take it from a professional wrestler or somebody like that, boxer or whatever, because they are a little bit tougher than the baby. Okay, so it takes more energy to do that. So here is the summation, the summarizing of this trend. Okay, so the word generally, you will find examples as you go left to right where it may at an instance decrease. Like, I don't know one in particular off the top of my head, but let's say, for instance, from this element to this element, the ionization energy actually decreased. That can happen, but the general trend is that it increases. Okay, that's why the word generally is there. Okay, or else to say always, but for the most part. So that's ionization energy. That's the first of the three today. The second one is the trend for elements for atomic size, okay? Or sorry, ionic size. So we talked about ions yesterday, right? And we mentioned that metal atoms tend to lose electrons and non-metal atoms tend to gain electrons. So the element sulfur is a non-metal. That means it's going to gain electrons. The element potassium is a metal. It's going to lose electrons, okay? And these last two bullets are very important here. Cations are always smaller than the atoms from which they form, and anions are always larger than the atoms from which they form. And really, it doesn't take too much thought to understand why. A cation is when you remove an electron. Same number of protons, you remove an electron. Okay? So you're removing an electron, and when you remove that electron, you have less electrons and you have the same number of protons, so the electrons are more attracted to the nucleus, so the ionic size gets smaller. Okay? And anions gain electrons. They either gain 1, 2, or 3 electrons, and occasionally I guess 4, but not usually. When that happens, they become larger because they have the same number of protons. Because an ion is still, it's an element, it's a charged element, charged atom, I guess. But it has the same number of protons, and now it has extra electrons, so it has more electrons than protons. So the radius, or ionic size, I guess, gets larger. Okay. So here's the trend. Ionic size tend to increase from top to bottom, and the size of cations and anions decreases from left to right across a period. Okay, so this is the same trend as atomic radius. Okay, same trend as atomic radius. And you can see these examples here. As you go down, okay, not only does the atomic radius get larger, okay, the ionic radius gets larger as well. Okay, that's an example right there. And metals that are representative elements tend to lose all their outermost electrons during ionization energy. Okay, so what this means, and you'll understand this more next unit, I feel. This means that they're going to lose the number of electrons it takes to get back down to the last energy level. These ions are going to do that. Okay, so like sodium would lose 1 electron. It's in group 1. Magnesium, it's in group 2, would lose 2 electrons, and something like aluminum, which is in group 13, would lose 3 electrons to get back down to the last energy level. Okay, and same thing here as you go down the group. Okay, for your ionic or your I guess I should mention this too. Look, these are the atoms and these are the ions. If you compare the cation to the atom, it's smaller. Okay, you see that these are smaller because they have less electrons. They've lost electrons. But here, these have all gained an electron. Okay, so these anions are larger than the atoms from which they come from. Okay, hopefully that makes sense. They're gaining something. Okay, if you gain weight, you're going to be larger than you were if you were to, lose weight. Same concept, just chemistry and not life, I guess. So here's something you can look at if you need to. And here's the summary of this trend. Okay. So what are trends for ionic size? If you've already written this down once, don't write it again. Okay. You should have, at this point, if you're watching this video, you should have already written it down once. Okay. So the last trend we're going to talk about today is electronegativity. And out of all the trends on the periodic table, electronegativity may be the most important. If I had to pick one, I would say it's probably the most important for the rest of the school year. Okay, so electronegativity is the ability of an atom of an element to attract electrons when the atom is in the compound. Basically, it's how well it can take an electron from something else, essentially. There's a scale that is used to determine these values. If you have, I don't have one with me, but you all know the periodic table that I've posted all year, the one that I've given you if you've been in person. You know that one I'm talking about. That periodic table has the electronegativity values on it. And what we do tomorrow is practice. We're going to look at that. Okay, so electronegativity is the ability of an element to attract electrons. So some elements have a high electronegativity. They're able to attract electrons. These are the values for these. Okay, now they're expressed in what's called Pauling units because Linus Pauling, nice name, was the man who came up with, he did a lot of work in ionization, energy, electronegativity, and came up with this scale that we still use today. So as you can see here, this is not all the elements on the periodic table. Okay, these are only selected elements. But if you notice, though, these are elements that are in the S. This is the S block, and these are the ones that are in the P block. Okay, those are called the representative elements because those are the ones that we care about more. Okay, so notice also we don't have the noble gases here. Why do you think we don't have the noble gases here? The reason we don't have the noble gases listed in terms of electronegativity values is because they don't want to attract electrons. Now, these elements over here, they don't want to attract electrons, and want is not like these things don't have fill-ins, but these are very unlikely to attract an electron, but they still could because their outer shell is not perfect. Okay, but noble gases are perfect, so they don't want. They have no indication of attracting any sort of electrons, so they don't have values for electronegativity. As you can see here, top right has the higher electronegativity values, and bottom left has the lower electronegativity values. So that might help you figure out what the trend for this is. But anyways, as you go left to right, it increases. As you go down, it decreases. Okay, so fluorine has the highest, oxygen is the second highest, and chlorine and nitrogen have the third highest, whereas cesium has the lowest. Okay, so here's the trend I just said. Electronegativity values decrease from top to bottom, and they increase from left to right across the period. So this is the fourth trend. Okay, the fourth trend. The two that decrease left to right, okay, that decrease left to right are ionic size and atomic radius. And the two that increase left to right are electronegativity and ionization energy. Okay, so, and I've already mentioned this, but you do need to write it. The least electronegative element is cesium, which has a value of 0.7. Okay, It has the least tendency to attract electrons. When we get to the eighth unit of the year, um, which deals with polarity, electronegativity is going to be very important. So that's why it's important to kind of understand, get a basis of what this is. The most electronegative element is fluorine, which has a value of 4.0. And here's the summarization of these trends here. Okay, but hopefully you've got that. And if you have already written this down once, which I'm sure you have because it was back here, okay, don't write it again. All right. So we're going to